Hello, my name is Joseph Dewey, and today I'm going to be continuing on with a short series of videos on the analog devices AD-ALM2000, also known as the m2k learning module. Today I'm going to be going into the signal generator and the oscilloscope features. I did an earlier video regarding its power supply capabilities and its voltmeter capabilities, so this is just a continuation on. So what we have here is the Scopy software. I'm going to double click on the device and choose to connect. If all goes well, it'll run through a calibration procedure for each item, and then we should be ready to go. So the first thing we're going to look at is the signal generator. Both the signal generator and the oscilloscope kind of go hand in hand with each other. You will need some way to generate signals to test certain circuits, and you also need to read various signals with the oscilloscope. So they're kind of one in the, you need them one and the same. So we'll open up the signal generator feature, and the signal generator here for the m2k is a two-channel device. They're single-ended. In other words, there is a signal lead and a ground lead for that channel. They can output a voltage, a signal voltage of plus or minus 5 volts to a frequency of 5 megahertz. That's within spec. When you look at the software, you realize you can go further than that, but they're only going to guarantee the plus or minus 5 volts and the 5 megahertz. Over that, you may be pressing your luck, and later on when we get more in depth I'll show you what can happen when you try to exceed those values. The signals are actually generated by a 12-bit 150 megasample per second DAC. Has a bandwidth of about 30 megahertz, which means you really can't generate a 30 megahertz signal, even though the software seems to be able to let you do that. In all reality, you can't. And you have a choice of 4 signals you can generate. One is a constant, which is, as it is, a DC voltage. And you can adjust it up to 5 volts or all the way down to negative 5 volts. So, in a way, you can use the signal generator as a third power supply if you wanted to. The only problem is it's extremely limited. The main power supply is limited to 50 milliamps. With the signal generator, it's even less than that. So it's not really recommended to use it as strictly as a DC power supply output. Second choice is waveforms, which is pretty much standard. You can get a choice of a sine wave, square wave, triangle wave, trapezoidal wave, rising sawtooth, and falling sawtooth waveforms. Right? For us, I'm going to leave it at sine wave. The third choice is buffer. What buffer is, you can actually read in a wave file, wave sound file. Also, you can read in, I believe, common delimited files that you can generate from Matlab, so you can put in your own complex waveform. And finally, math. So you can actually enter an equation here to generate a signal. So those are the 4 kinds of signals that the m2k can generate. So pretty much that's the simple portion. Next, we're going to go into how to deal with the oscilloscope. Okay, to look at the oscilloscope, we'll click on the oscilloscope feature. And the oscilloscope itself is made up of 2 differential channels that can measure a signal that's plus or minus 25 volts. The key thing is it's a differential channel, and I'll get more into that later. The signals are measured by a 12-bit 100 megasample per second ADC with a bandwidth of 25 megahertz. Again, much like the signal generator, that does not mean you can measure a 25 megahertz signal with this device. Rule of thumb, and it's the same rule of thumb that you would use with a regular full oscilloscope is you take that bandwidth, in this case 25 megahertz, and usually any oscilloscope will be good for about a third of that. So for a 25 megahertz signal, you would probably be able to read 7 megahertz in. And what that mainly means is if you were to look at a 7 megahertz signal, once you get to that point, it should be down by 3 dB. In other words, if it was a 1 volt RMS signal, it would be down to about 0.707 RMS. So that's the usual rule of thumb to use for any kind of oscilloscope. When you see that bandwidth number on oscilloscope, take about a third of that as a good input signal. Over that, you're going to see some signal degradation. So that's the rule of thumb to keep in the back of your mind. One other thing you want to remember about the m2k is the oscilloscope inputs are the same as the voltmeter inputs as is the spectrum analyzer inputs. So in other words, you can only use one feature at a time. You cannot use multiple features. Okay? Now we'll go into wiring up the oscilloscope and then running the software. So for using the oscilloscope in our situation here is I've taken the waveform generator channel, which is the yellow wire, and I've hooked it up to the channel 1 input for the oscilloscope. Also, I've taken the ground pin. Remember, the waveform generator is signal ended, so in other words, it has to be a ground connection for it. And I've wired that into the negative terminal of the channel 1 oscilloscope. Again, the oscilloscope is a differential measurement. So this other lead on the oscilloscope, which would be labeled a 1 negative, is not actually connected to ground. And that's one of the differences from a benchtop oscilloscope. When you use a benchtop oscilloscope with a BNC connector, that metal portion of the connector, the outer shell, is always attached to ground, where in this case it is not. It's a floating measurement. And you can use that as a good tool for certain experiments. Okay, now that we have the m2k signal generator wired to the oscilloscope, let's use the signal generator to generate a standard signal, let's say a waveform, sine wave. I'm going to set that for 2.828 volts peak to peak. And when you keyboard enter a number, you must hit enter key for it to be locked in. The next thing I want to do is I want to adjust the frequency. For our case, I want to set it to a frequency of 10 kilohertz. Now these frequencies and amplitudes, you can adjust them using the knobs here. As you can see, you can adjust it up and down that way too, using the knob and your scroll wheel on your mouse. Okay, so right now I've set it again for 2.828 volts peak to peak with a frequency of 10 kilohertz. I'm going to click Run. Now I'll go over to the oscilloscope feature. I'm going to click Run on that and turn it on. And you'll see on channel 1, which is the orange color, part of our signal. We also have channel 2, since it is a 2-channel oscilloscope. It's hard to see, but that's registering 0. So I'm going to shut that off. That way it's out of the way. Now, because I'm not seeing the full waveform, I have to adjust my time base. And I'm going to increase that up to, since it's a 10 kilohertz signal, at least 20 microseconds. Go up to 50 microseconds, but I think we'll stick with the 20 microsecond setting. The rule of thumb is you want at least 3 cycles of the waveform on the screen. That way you verify that you have valid data. One other rule of thumb is you want to take as much of the vertical space as possible. Right now it's set to 1 volt per division. I'm going to set that to 500 millivolts per division. So there we go. Now we see our sine wave at a particular frequency, and you can do the old-fashioned way by counting divisions. So we said it's a 10 kilohertz wave. So 1, 2, 3, 4, 5 divisions at 20 microseconds per division. So there is 100 microseconds. One over that, and you should be able to get your 10 kilohertz. As for the voltage, we said it was 2.828 volts peak to peak. We are set for 500 millivolts per division. So we have 5, 1, 1.5, 2, 2.5, and almost 3 volts. Again, because it's an odd number, you would have to line it up exactly with the grid line. So what you can do now is to find out the specific information. You can click on the measurement feature. And by default, it'll give you the period, the frequency, the peak-to-peak amplitude, and the mean voltage. And we see we do have our frequency of 10 kilohertz with a peak-to-peak amplitude of 2.86, and it's kind of noisy there for the numbers, close to what we set for. If I click on this button here next to measurement, it brings up the measurement settings window. And right now, like I said, by default, it gives you period, frequency, peak to peak, and mean. You can go to custom selection and change some of your settings. So for the horizontal, which is your time base, you have here period, frequency. You can measure rise time, fall time, pulse width, and duty cycle. For us, I don't need to change any horizontal measurements, but I want to take a look at the vertical measurements. And in the vertical measurements section there, we can measure min, max, peak to peak, which is on, the mean, which I have really no use for. I'm going to shut that one off. I'm going to measure the AC RMS voltage and choose that. And now you see here, I have my information, and I chose the peak-to-peak value of 2.828 because that will represent pretty much 1 volt RMS. And I'm pretty close to that. Right now it's saying I'm at 986 millivolts RMS. So that's one of the features for all oscilloscopes, whether they're bench mount or the digitizing USB style. You can do measurements so you can get the precise information. I'm going to shut that feature back off. Another feature is cursors, where you can use cursor measurements to take your measurements. So I'll move one cursor here, and that's gray box there, and then I'll pull this one down. I'm holding on with my left mouse button, pulling down. And now I'll see my voltage difference between that cursor and that cursor. The top and bottom is about 2.83 volts. Also, if I want to measure the frequency, move it over here, find out where it crosses the zero line, take that cursor there, move it across. It'll tell you the differences in the cursor locations, the time, delta, and in turn the frequency. So those are cursor measurements. If you don't have a default measurement feature that will fit your needs, you can use cursors. The next item I want to look at is something called triggering. Turn that menu on. And right now the trigger level is set to 0. That means it's this box here on the 0 volt line. And we're triggering on the rising edge. If I go to the condition, I say I want to trigger on the falling edge, the waveform seems to have moved and flipped. Okay? I'm going to go back to rising edge real quick here. And I'm going to address the trigger level. So you see right now, the trigger level is set to 0 volts. So right there at the 0 zero portion, 0 time, 0 voltage is where it's being triggered. I pull up on the trigger point. You should notice the waveform seems to be walking towards the left. So right now I'm set at a trigger level of 1.384 volts, right there. Some students will complain that their waveform seems to be dancing all the time, and that is usually a problem that it's not triggered properly. So you would go into your trigger memo and you see right now the trigger level is set for a positive 1.8 volts. We know our signal is mainly almost peak to peak of 3 volts, so we're above that. So we can pull our trigger level down, and now our wave will stabilize. I usually just leave it set for 0, and that seems to handle most problems. I'm going to turn on the channel 1 features again. One other thing probably should mention here, we have settings for channel thickness, and this is, how thick do you want the trace to be. I usually leave it for the default of 1. Curve style, in this case, since it's such a high frequency waveform of 10 kilohertz, you will not see too much if we choose dots or even steps. The most traumatic would be sticks, which almost gives it like it's filling in the space under the curve. Go back to standard lines. One other thing that you can try is something called AC coupling. And what that does is it will block any DC voltage on your signal. In this case here, we'll go back to the signal generator. And like it says, we have a sine wave with an amplitude of almost 3 volts peak to peak at a frequency of 10 kilohertz. I'm going to make a change. I'm going to change the amplitude to something like 100 millivolts. And it's hard to see, but you can see a little bit of the waveform there. But I'm also going to apply a DC offset to it. I'm going to set the DC offset to 2 volts. So now I have a 10 kilohertz sine wave with an amplitude of 100 millivolts peak to peak riding on top of a DC signal of 2 volts. Take a peek at it with the oscilloscope, and now you'll see a sine wave offset by 2 volts. 1 volt, 2 volts. Now, if I just want to look at that sine wave by itself, by turning on AC coupling, I eliminate the DC component. So this is a way that you can see if you have an AC signal sitting on top of your DC signal. I'm going to go back up to the top here and adjust the millivolts per division downward. So I've adjusted it all the way down to 20 millivolts per division. You can actually see the digitizing portion of the A to D that's in the system. See if we change it to dots now. You'll notice now, instead of it being a solid line, you just see the dots. Try steps. It's hard to see any real difference. Smoothing feature, it'll smooth it out slightly, but really no major difference. Back to lines. So that's what AC coupling is about. When you finish with it, turn it off, because you never know. You may see an AC signal that is sitting on top of a DC signal. If AC coupling is on, you will miss that. Okay? So that's some of the features of the signal generator and oscilloscope. Now we'll take a look at some of the other features. We'll go back to signal generator here. And I had mentioned earlier that the oscilloscope has a bandwidth of 25 megahertz. But in all reality, you should only be able to measure cleanly anywhere from 5 to 7 megahertz for your signal. And what we're going to do is a little test of that. I'm going to switch from a sine wave to a square wave. I'm going to eliminate the offset voltage, set that back to 0. I'm going to set the amplitude to volts. I'm going to set it to 2 volts peak to peak. Okay. Right now my frequency is set to 10 kilohertz. I'm going to set it to 1 megahertz. Take a look at it, the oscilloscope again. Okay, as you can see we're slamming, so I have to adjust my voltage per division. Adjust it again to about 500 millivolts per division. And of course now I'm generating a 1 megahertz sine wave, square wave, so I'll have to adjust the time base down. And now you start noticing some 100 nanoseconds is the fastest time base I have. And if you look closely, you'll see ringing here on the signal. This is where the bandwidth of the oscilloscope comes into play. And in this case, we also have to deal with the bandwidth of the signal generator. In all honesty, this ringing here, I'm not sure if it's coming from the generator portion or the oscilloscope portion of the equipment. And when you increase the frequency, say let's go up to 5 megahertz on our square wave, you see it becomes more pronounced. And that's the bandwidth issue there. The bandwidth is what we call the 3 dB point, or where your signal is down from its maximum to 0.707. So if you had a 1 volt RMS signal, you would actually see 0.707 volts. So those are key factors to keep in mind, whether you're using the USB digitizing style of oscilloscope or a piece of bench equipment oscilloscope. You have to look at that bandwidth, and like I said, rule of thumb is only a third of it is good for actual measurements. Now let's take a look at some other signal generator features. Okay, one of the other features of the signal generator is the ability to produce math functions. And what I'm going to do is throw together a quick math function. Let's say 2 times, open parentheses, cosine wave. That's going to be 4 times the base frequency. In this case, it's 100 hertz. Close parentheses. That also is going to be multiplied by sine function. And that's just going to be the straight frequency. And then once you've entered that, you should hit apply. Now if you've made a mistake, this line here will turn red. And it's obvious I've missed a parenthesis, closing parentheses. So close off, hit apply, and that's the actual waveform that's being generated by the math. I'm going to go over here to the oscilloscope, and I'm going to make some adjustments. And well, actually I'll try something called the auto set feature and see what that does for us. There. Auto set is an attempt at auto scaling. It'll work some of the times and not all of the times. Usually when it's a very small signal, it won't work. And here we go, we see our signal, and we see the problem of triggering here because it seems to be jumping and dancing across the screen. activate the trigger menu, right? And what I can do is right now the trigger level, when you do auto setup, it'll try to determine the best triggering level. For some reason it's chosen a negative 36 microvolts. I can try to set that for 0. And again, it's still dancing. It's looking at rising edges, and there are a lot of rising edges there that are not exactly the same. It's not a 100% repetitive waveform because it has different frequency components. So this is one of those cases where you're better off just dragging it up. And what I'm going to try to do is catch on to one of the peaks of the signal right there. And now that seems to be stabilized. I can move it down a little bit. Still relatively stabilized because here I'm seeing that peak and that peak, or rising edge and that rising edge. If I move a little bit further down, now you can see that it's dancing again. And the reason why that is, pull back up so I'm just triggering there. It's looking at this rising edge, and this point here is the same amount of time to that point, the same amount of time to that point. When I was a little bit lower, I was catching that rising edge along with that rising edge, along with that rising edge, along with that rising edge. But each one is spaced differently, so it would have problems triggering. We'll go back to a 0 setting for the trigger. Okay. And one other feature you can do here, right now it's in continuous run. You can do a single trigger. And what that will do is take the first rising edge it sees, fill the screen, and freeze it. So it's no longer taking any more information. If you notice here, the green arrow is gone, so it's done. It's one shot and it's done. Set it back up for continuous running here. So that's some of the features you can get from the signal generator using math functions. I'm going to go back to a waveform again, and this time I'm going to set it back to a sine wave. Amplitude 2 volts peak to peak. I'm going to set the frequency down to 10 kilohertz. Go back to the oscilloscope. Get out of the trigger menu and go back to the channel 1 menu. Adjust the time base down so I see my actual sine wave. Going to get a little bit closer in. So there we see our sine wave that's being generated. 10 kilohertz, 2 volts peak to peak. And what you can do is actually add noise to the signal. A uniform noise, Gaussian noise, Laplacian, or impulse. We'll do a Gaussian noise, set for 1 microvolt. I'm going to set that to about 100 microvolts. And it's really hard to see on the oscilloscope by trying to zoom in some more. Again, it's kind of imperceptible. Let me go back to the signal generator. Set it for 100 millivolts. Now I've added a noise signal to the output of the signal generator. So that can be helpful to see if you're going to do some sort of noise filtering circuit. Of course, when you start looking at the signal at, let's say, normal values of 500 millivolts per division, you will lose that noise signal there, that you won't be able to see it. So that's some of the features of both the signal generator and the oscilloscope. I'm probably going to do another video that'll explain a little bit more about the scope's ability to do differential measurements. Thank you, and have a good day.